All right, this gets a bit more complicated and technical. Now, please listen very carefully to my advice. Some of these problems are going to make sense and they're going to be very straightforward conceptually. I know you're smart enough to figure this out in your head. What I'm doing is training you for the more difficult problems that you will not be able to do in your head. So I want to go ahead and begin you on good habits so that you can be successful. You must always make up a formula for these problems. There is no formula. Okay, you can look anywhere on Google, you can look anywhere on Khan Academy, on YouTube. There is no official formula. Whatever you do, you'll find the rule that we've talked about, right? The equilibrium rule. And so for problem 7, we're going to show you how to set up the equilibrium rule. It gets a lot more complicated. These are very simple problems on purpose. I want you to be able to learn how to set things up. The formula always depends on the situation. Some of you will begin struggling very much with this class in comparison to the past. You're going to struggle a lot now. I would suggest if you want to get over the struggle, please, please, please heed my counsel for problem 7. Do the setups, do the things I want to show you. Here we go. Problem 7. You got to do 3 things for each problem. You must draw a free body diagram. You must set up Newton's first law, and then you must solve it. Meaning you're going to get an actual number answer. In an attempt to move a box, a child exerts 30 newtons of force on a box. So let's go ahead and draw this. Draw this. So here's the floor. Here's the box. Draw the belly button. Okay. 30 newtons of force on a box. So let's say, here's 30 newtons of force. The box does not move. Okay, if it does not move, that means it's equal to 0. Okay, this is Newton's first law. What is the value of the frictional force? Frictional force is a resistive or opposing force. In other words, if there were no friction, this box would have moved. Okay, imagine moving a box on a frozen ice lake. Okay, it would move easily. But because it's not on a frictionless surface, there will be some opposition. And in this case, the box did not move. So you have that force going this way, but you have another force going this way. They didn't give us a number, but I'm going to call this the frictional force. Usually for friction, we use a lowercase f. We want to find out what that frictional force is. When it comes to problems like these, we usually pick a positive and a negative side. So in this case, I'm going to make the force be positive, and friction is usually going to be opposite, so that'll be a negative. So in this picture, going to the right is positive, going to the left is negative. You'll notice that this arrow is going to the right, and therefore this value is positive. You're going to notice that this one's going to the left, and therefore it's going to be a negative. Number 1 is done. Part A, number 1, we drew a free body diagram. Great. Part 2, let us set up Newton's first law. Newton's first law states the following. It states that the sum of the forces along the x-axis is 0. We're using the x-axis because the x-axis is when you move things left and right. The y-axis is when things are moving up and down. In this case, the object is moving left and right. So we want to add all the forces along the x-axis and make sure that they're balanced so that it's equal to 0. This is not the setup yet. This is the rule, right? The setup would be this. Notice you have how many forces do we have acting on this box? If you're not sure, let me ask you this. How many arrows do you have on this box? So what you could do is just make some blanks, if it helps. You make the number of blanks depending on how many arrows you have. We have 2 arrows, so I have 2 blanks. The first blank will be that positive 30 newtons, and the second blank is going to be that minus F. It's very important that you have good Algebra 1 linear solving linear equation skills, and we're going to really develop that in this class. I want to get the F by itself. I'm going to add F to both sides. These cancel out, and I'm left with 30 newtons equals friction. So in this case, the answer is, and that's green, that should be in green. Sorry, that was the third part. We already solved it. So the frictional force is 30 newtons. Now you think to yourself, that makes sense. Because if this thing isn't moving, if it's balanced, whatever you give it is whatever it takes. It makes sense that it would be 30 newtons. Remember, all of our answers need to make sense. Now that you look back, it's an obvious answer. However, I want you to get in the habit of drawing the free body diagram, setting up the rule, and then solving it. Part B, why don't you try it out? Pause me and try part B. I have a box being pulled with 10 newtons and it has a friction opposing it. I'm going to make this be positive, this be negative. These are not all the problems are going to be the same, folks. Always set things up, always draw things out. We have the sum of the forces along the x-axis is 0. We have two arrows, okay? We have two forces. I have a positive 10 newtons minus a friction equals 0. And if I add friction to both sides, I get what we expect, that the friction is equal to 10 newtons. I would consider that you pause me and think about part C for a bit and see how far you get. We have three forces working here because there's three toddlers. Two of them pull to the left, one pulls to the right. So here is our stuffed animal. There's two of them going this way, and they're not the same force probably. So that's why I'm drawing them different. Okay, if you draw the arrows the same length, that means that they're equal. So it's very important that you draw these carefully. One of them is pulling it to the right. So the one of them pulling to the left is 15 newtons. One of them pulling to the right is 37 newtons. This one we don't know. I'm going to call this F. This is first law because it's motionless in the air and they're balanced. That's why it's equal to 0. So the sum of the forces along the x-axis is equal to 0. We want to find that third value of that force. So again, I know you can do this in your head, but we need to get you in the good habit of setting these up and understanding what goes where and why. So we need to pick a positive side, we need to pick a negative side. We have so far made the right side be positive, but is that in our best interest this time? It'll still work if you want, but I'm going to make the left side be positive because I have two forces going this way. And in particular, I'm looking for F. We're going to solve for F. So if it's negative in this case, it's going to add an extra step to our work. If I make left be positive this time, then I'm going to make right be negative. Every problem is different. All right. Sometimes we might actually want to make the right be positive and the left be negative. How do you know? You just know by doing a lot of these problems, okay, and by experiencing it. So I'm going to go ahead and notice that I have three forces this time. Okay. I'm going to start with my positive. So I have a positive 15 newtons. I have a positive F, which I'm looking for. I have a minus 37 newtons, and that's equal to 0. Notice that with first law, the right side is always 0. But the left side is where I collect all of the forces. Some of them are positive, some of them are negative. How do we know? Is by drawing the free body diagram and picking some sides and making some decisions. We go ahead and combine these two. I get a negative 22 newtons. And then if I add 22 to both sides, and why am I adding 22 to both sides? Because I want to get this F by itself. So we're solving for F. F equals 22 newtons. So the mystery force is going to be 22 newtons. Part D. A large piñata with a weight of 30 newtons hangs from a beam by a massless frictionless string. So here we go. Here's a ceiling. Piñata. But there's another piñata attached to it that's smaller. Now you'll notice that this time we're not talking about things on the floor that are being dragged. These are things that are hanging from the ceiling. So instead of the x-axis, this is going to be the y-axis. So y-axis because things are going up and down, okay, instead of left and right. Now let's be careful here. I'm going to call this object number 2, and it's going to be object number 1. Object number 1 has a weight of 70 newtons. Belly button, 7 newtons. And since we know the string is going to be tight, there's going to be a tension 1 going on it. Okay. Now before you get all crazy and happy when I start doing both of them at the same time, when it comes to Newton's laws, we have to take things apart bit by bit. So I'm going to go ahead and as far as we're concerned, this doesn't exist. Okay. For now, it doesn't exist. I want to just focus on this one right here. So if I set up Newton's first law for this, we have to pick a positive and a negative. In this case, I'm going to pick down to be positive and up to be negative. It doesn't matter as much because this thing is not moving at all. It's just staying still. So we could have picked up positive and down negative if you want. I'm going to pick it this way. In this picture only, I have two forces. I have the 7 Newton weight going down and I have the tension 1 going up. So I have positive 7 newtons minus tension 1 is equal to 0. If I solve for tension 1, I get that 7 newtons is equal to tension 1. So you know that tension 1 is 7 newtons. Okay, I'm going to put that somewhere here. Tension 1 is 7 newtons. We knew that already before, but I want you to get into the habit and the practice again of setting things up right. But remember, there was a piñata up here. Now, let's try this again. Piñata number 2, right? Piñata number 2 had a weight. This is going to be a little tricky to draw. It had a weight going down of 30 newtons and has a tension going up. We'll call this T2. However, remember there's a string down here, right? There was a string down here. And this string had a tension 1. That tension was due to the bottom piñata. So you have a tension on the top string and a tension on the bottom string and the piñata in between. Now this tension is actually pulling the piñata downward in this case. Let me draw these with different colors and let me kind of explain that again. We know that the object itself has a weight of 30 newtons. We know there's a tension up here. But from the previous problem, you would recall that there was a piñata down here that weighed 7 newtons, and that was providing tension to the string right here. In the previous drawing, the tension was going upward because it was opposing the weight of this object. However, with this object out of the picture right now, we haven't deleted it, it's not gone, it's attached, but we don't want to focus on it right now. We recognize that this string has a tension. If this string has a tension, that means it's pulling down the object. If it's pulling down the object, that means if this tension 1 is pulling down the object, then that means tension 2 is receiving more tension because of tension 1 is also bringing it down. If we set up Newton's first law along the y-axis, we have 3 forces this time. And I would suggest making the bottom be positive because we have 2 forces going down and 1 going up. So then T2 will be negative. T1 will be positive and the 30 newtons will be positive, right? 30 newtons is the weight of the piñata. So remember T1 was 7 newtons. So I have a positive 7 newtons and then I have the weight plus 30 newtons, check. And then I have a minus T2 equals 0. Remember the left side we collect all the forces and it depends on which way they're going. Combining these, we get 37 newtons. We move T2 over and we get a value of 37 newtons for tension 2. Notice, like the Moulin problem, that the tension in the top string is due to the combined weights of the entire system. For your summary, explain how to set up the equilibrium rule. Try to use the words for this. How do we set up the equilibrium rule? Try to find a pattern for the last 4 problems that we did in this video. Okay, explain how to set up the equilibrium rule.